Hello everybody, in this video we'll be running our first OpenFOAM tutorial. So this is going to be lid-driven cavity flow, or it's called a cavity tutorial. So this problem, the geometry consists of a 2D square where the left, right and bottom are just standard non-moving walls. So the velocity is 0, whereas the top wall is moving at a velocity of 1 meters per second in the x direction from right to right. So you can imagine maybe like a conveyor belt on top, so the bottom is running across it. So it's causing the fluid to rotate in this direction. For our mathematical model, it's going to assume incompressible laminar flow. So the Navier-Stokes equation will take this form in terms of our conservation momentum and our continuity equation. So the two unknowns are the vector velocity here, v, and the scalar pressure. So OpenFOAM actually puts this rho as part of P, so P over rho. So for the incompressible solvers in OpenFOAM, they actually don't solve for pressure, they solve for kinematic pressure, which is just P divided by rho. Okay, so I'm going to jump across to Windows. So first thing, if you've installed Ubuntu through the WSL, so you should be able to find the Ubuntu app, open it up. And then within that, I'm assuming you follow previous videos, so you've installed OpenFOAM within that environment. So when you first open up the Ubuntu, if we were to write, say, simple foam -help with a space -help, then it should give us a usage details like this. So that means OpenFOAM is installed correctly. Okay, for the first tutorial, just before we get to actually running this cavity case, there's a couple of things we're going to do, because I'm assuming this is the first time you're using OpenFOAM in this setup. So for the models, we're going to keep them all in a directory called the run directory. So that directory doesn't actually exist yet. So we're going to run a command make dir to make a directory, and then $run like that. But just before $run, we're going to go -p. So what are we doing here? If you've done the Linux tutorial already, some of this will make sense. We're going to make a new directory. The second two parts may not make sense. So the capital foam run. So anything starting with a dollar is called an environment variable. So it's basically like a variable that has been defined in the shell environment. So it'll be all capitals and starts with a dollar. So dollar means use the value of this variable. So OpenFOAM defines a bunch of these environment variables, which allow you to easily navigate to key directories within OpenFOAM. So this foam run is the location of this run directory we're going to make. And -p is -parent. So make directory, if you try and make a directory, it'll do that. But if I try and make a directory and I give address to a directory where its parent doesn't exist. So for example, in the current directory, I want to make a folder called folder A and a folder called folder B inside that. So if I directly try and make folder B, it'll say, well, folder A doesn't exist. So -p means create any parent directories that you have to as well. So if foam run doesn't exist, create that. But if the parent directory doesn't exist, create that as well. So if I press enter on that, and that will do that. So if I just go cd $foam run, I can actually go to that directory. So if I print working directory, you'll see what it's done is in my home folder, there's a directory called OpenFOAM, and I'm using OpenFOAM 9 here. So it makes a directory called philipc-9, which is my username, and a directory inside that called run. So I could have easily just press cd to go to my home directory. I go inside the OpenFOAM directory. Remember pressing tab to autocomplete. ls, I can see there's OpenFOAM 9, third-party 9, so that's the OpenFOAM installation, and you'll see beside that it's basically created a user directory. So for all my files and models, they're not going to be stored in the main OpenFOAM installation directory, they're going to be separately stored in my user directory. So philipc-9, so this, they've set it up so if you have multiple versions of OpenFOAM installed, you can have separate directories for them. So philipc-9, and then ls, you can see that's where our run directory is. So rather than typing cd foam run, they've also made a shortcut in OpenFOAM. So if you just type run is an alias. So an alias is just anytime the terminal sees the text run, it just replaces it with cd run. So if I go cd, it goes back to my home directory, type run, enter, I'm back in the run directory. So there's nothing there at the moment. Just if it helps, you can open an explorer.exe space dot, means open the current directory. So you can see where we are here. So if I go back to my Philip C home directory, you can see there's hidden files that Linux isn't showing by default. So if I go inside OpenFOAM, Philip C9, and run directory, that's the directory. We're going to put all our models in here. Okay, so OpenFOAM actually comes with a bunch of models already set up, and OpenFOAM calls those models cases. So a model in OpenFOAM isn't a file, it's actually a directory with files and folders and or directories inside it. So we can navigate to those by using another environment variable. So if we go cd $foam tutorials, like that, if I go enter, that will bring me to, you see it brought me to OpenFOAM 9 tutorials, and this is where they're all stored. So if I type ls, you'll see I have a couple of files here for if I want to run them, but you'll see there's folders or directories, DNS. So when we do turbulence modeling, you'll know what DNS is. Some basic PDE solution methods like a heat equation. There's combustion solvers, compressible solvers, incompressible solvers, heat transfer solvers, particle methods, multi-phase, so if you've like liquid and gas, stress analysis, and then there's some other random things as well, like solving the Black-Scholes equation, which is a financial equation. And so we could go in and run the cases in these directories, but then if we break the cases, then they're broken. So it would be better if we just make copies of these into our run directory, and then we can mess around with them in the run directory. So that's the strategy we're going to take. Incidentally, if you want to see the value of an environment variable, there's a command called echo. So if you echo an environment variable like foam run, it just tells you what that environment variable is set to. If I go foam tutorials, tab it, you can see what that's set to. If I go foam underscore and then I press tab, there's multiple autocompletions. So if I press tab a second time, it actually just shows me all the different environment variables set by foam or OpenFOAM. So you can see there's run, there's lots of other things to do with the installation, which we don't really care about. So for example, solvers, you can see where all the solvers are, or utilities, which we're going to talk about. So let's go back to the run directory and we're going to copy this cavity case in. So we're going to go copy CP, and it's a directory, so we need -r recursive. We're going to go foam tutorials, press tab. So typically in Linux, we can go /, and if we go tab here, it should replace that environment variable with the full name, so we can actually copy from it. But in this case, and sometimes in Linux to do with a bug in later versions of Bash, the interpreter, this can happen. So if I just delete that / that appeared, and in this case, in my Windows shell, I have to do this anyway. If you press escape, then let go of escape, and then press Control E on the keyboard. So what I did there was I just pressed escape and then let go of escape, and then holding Control, I press E on the keyboard, and that will replace the environment variable in line with me. So that's fine. So then I'm going to go incompressible, so INC tab, and then the way they've broken it down, if I press tab twice here, it's broken down by OpenFOAM solver. So in OpenFOAM, there isn't just an OpenFOAM application. It's not like Fluent or Abacus, but instead there are many different applications or executables. So if you want to solve incompressible flow, there are a bunch of solvers you may choose from, whether it's going to be steady state or transient. So in Fluent, we could choose a coupled algorithm or a simple algorithm or piezo algorithm to solve the governing equations. But in OpenFOAM, they're all different solvers. So you'll have a simple foam, a piezo foam, or like a coupled solver foam. And the way the naming convention adopted is if it ends in the word foam, it means it's a solver. It means it solves some governing equations for partial differential equation. So to begin with, we're going to use Eicofone, which is an incompressible laminar transient fluid solver. So type Eico tab, Then tab again. So these are the Eicofone tutorials. So they've given us two. One's called cavity and one's called elbow. We're going to take the cavity one, press tab. And inside cavity, they actually have a bunch of versions of cavity. So we're just taking the one called cavity. So you can see the full address here, Eicofone, cavity. So that's the directory we want to copy. And we're in our run directory at the moment. So we just want to put it where we are. So space dot. So cp-r, because it's a directory, we're copying this full directory, and then we're putting a dot in our current directory. So if I type ls now, you can see I have this cavity directory. cd inside this cavity, print working directory, you can see I'm now inside this cavity directory and run ls. So you can see there are three directories, 0, constant, and system. So let me just jump back to the Explorer here just to give you a different perspective. So here's our cavity directory. So this is called a case in OpenFOAM. So this is an OpenFOAM model. It's this directory. And the way you know it's an OpenFOAM model or an open case is all OpenFOAM models will have at least 3 directories or folders inside, a 0, constant, and system. So 0 represents time 0, and constant are meant to represent things that are constant about your model. So for example, the mesh and material properties. And then system is to do with different settings, like the time settings, like time step settings, and discretization or solution settings. So if we look inside each of those in turn, so either I can do it if you prefer, you can do it in the graphic environment here. These are all text files. So OpenFOAM is just, each of these directories will just have text files, so you can open those up with Notepad or whatever. But I'm just going to stick to the standard OpenFOAM way of doing it in the terminal. So first I'll go inside 0 directory. It has 2 files, U and P. So U is capital U is velocity, not in OpenFOAM. So V is not used for velocity. So U is used for velocity, and P is pressure. So these files are where we specify the boundary conditions and the initial conditions for the U field and the P field. So they're the 2 solution variables. They're the 2 unknowns in our governing equation, Navier-Stokes equation. So the text editor we're going to use is Emacs. You can use another one. You can use Notepad or Notepad++, whatever you want. So I'm just going to use Emacs. So we go Emacs U, and that will open up the file. So there are some comments at the top, and there's always this standard header, but then the main content of the file is here. So basically, each of these fields in OpenFOAM, it'll have the dimensions or the units. So these are represent this SI base unit, 7 SI base units. So the first is kilograms, meters, second, and then degrees, and then the last 3 are very rarely used. So in this case, this file is no kilograms, so it's meters to the power of 1 and seconds to the power of -1, so meters per second. So you can see this represents a velocity, meters per second. And this internal field uniform, this is the initial conditions for the velocity field. So it's initially 0 everywhere. So if you wanted to have non-zero, you could have to change that number. And then the boundary conditions are specified here. So there's a moving wall, a fixed wall, and then front and back, which we'll talk about later. So the fixed walls are no slip. There are the 3 sides. And the moving wall at the top is velocity in the x direction of 1 and 0 in the y and z direction. So this front and back and why there's a z direction, we'll see when we open up the model in Power View that OpenFOAM treats 2D models as a special case of 3D. So it's basically OpenFOAM models in 2D are just 3D models with 1 cell thick, and the front and back have a special boundary condition called an empty, so it doesn't solve in that direction. So you can close out of Emacs, so holding control, press X, and then C. So holding control, and then X and C. We can check the P file. Looks very similar. Different boundary conditions. The initial condition 0, it's a scalar in this case, not a vector. The dimensions are meters per second squared. So that you can check that corresponds to pascals divided by density. So pascals in SI base units would be kilograms per meter per second squared. Then if you divide that by meters, kilograms per meter cubed, then you'll get meters squared per second. So this is kinematic pressure. It's pressure per unit density. And the boundary conditions here on what as is typical on walls and as what Fluent will be doing is you set a 0 normal gradient of pressure at the boundary. So you don't know the value of pressure on a boundary. So in that case, you set the gradient of pressure to be 0. So that just means that if you're plotting the value of pressure away from the wall going into the fluid, that just close to the wall, you're assuming that it doesn't vary as you go away. So holding control, press XC to close the file. So that's the 0 directory. Go into constant, ls. There's only one file, transport properties, and something called new is defined. So this is our viscosity. So in this case, it's actually our kinematic viscosity. So it's viscosity divided by density as well, which is typical for incompressible fluid solvers. So suppose our true dynamic viscosity is divided by the density. So you can see 0.01, and the units which let you check what type of viscosity it is, whether it's kinematic or true, are meters squared per second. So you can check that against what you'd expect it to be. So in that case, that's like Pascal seconds will be dynamic viscosity, so it's divided by density here. So let's close out of that, go into the system directory. That's the last directory to look at. We've four files in this case. So there will always be 3 of these. There will always be control dict, this FE schemes, which is finite volume schemes, and FE solution, which is finite volume solution. So if you open up the control dict, we'll come back to this, but it basically lets you specify the start time, the end time, time step, the right interval is how often the results are written. And there's some other settings as well. If we were to look at FE solution and FE schemes, which we'll come back to, FE solution is to do with what methods are used to solve the linear equations, say for P and U. And in this case, Eicofone uses this piezo algorithm. So there's some piezo algorithm settings. So the defaults are fine for now. And then we can check FE schemes. And FE schemes are to do with whether you're picking first or second order finite volume discretization schemes. So like many of the tabs you would have skipped over in Fluent, basically the same methods we can choose from here. Okay, so how do we run this case is the next thing. So in this case, we have to make a mesh and then run the solver. So the case and boundary conditions and all the settings are set up. There's no mesh here yet. So there's many ways to make a mesh in OpenFOAM, and we'll talk about that later. And then later tutorials and lectures. But in this case, we're going to use one of the simplest methods, which is called block mesh. So there's a utility in OpenFOAM called block mesh. And by utility, I mean there's a command. So commands that end in the word foam, like Eicofone, are solvers. They will solve partial differential equations, whereas utilities won't end in the word foam. So block mesh is a utility. So block mesh will look for this block mesh dict. So we didn't open up that block mesh dict, but I can do it now. So system block mesh dict. So this is specifying the coordinates of the corner of this block and how many cells are in the X and Y direction. So we're going to have the next tutorials are going to be about how this block mesh, how do you actually set up this block mesh? In this case, it's already set up. So if we just type the command block mesh, press enter, and it's pretty quick. So if I scroll up, you can see what it did. It prints out some heading information about what time it is and the OpenFOAM utilities. You can see all the OpenFOAM utilities and solvers will print this little heading at the start, the version of OpenFOAM you're using. And then it'll say, doing a bunch of stuff, basically making the mesh. So that's the mesh made. How do I know the mesh is made? Well, if I ls the constant directory, there's now another directory present called Polymesh. And Polymesh is a polyhedral mesh because all OpenFOAM meshes are treated as polyhedral meshes. So that directory, if I ls inside it, the files inside it are their actual mesh that are created by block mesh. So maybe if I jump back here to the graphic environment called constant Polymesh, you'll see these different files, points, faces, and then this owner, neighbor, and boundary. So basically the way the mesh is defined is you have a bunch of points, so I can open it up, constant Polymesh, points. This is literally just a coordinate of every point in the mesh. There's 882 of them in this case. Faces then, just 1600 faces. And it's basically the first face says it has 4 points in it. And the 4 points are 0.1, 22, 463, and 442 in the list of points in the point file. So that's how they create the mesh. So faces are just lists of points. And then you have cells, which are just lists of faces. But the way OpenFOAM works is it does something called owners and neighbors, which are an alternative way of defining cells, which we won't get into. Okay, before running it, we're going to open the case in PowerView. So how do we do that? So I'm assuming you've PowerView installed on your Windows. So for PowerView to open this case, it needs a file to open, but this is a directory. So PowerView doesn't know what to do with that. So there's a trick to get it to work. So if you just make an empty file with an extension .foam, then PowerView, and if you put that in the main case directory, then PowerView will know it's an OpenFOAM case and knows how to open it. So how do we create an empty file? Well, we can use Emacs, but there's a quicker way. If we just go touch.case.foam. So touch is a Linux command that lets you touch a file, which basically just means update its last edit date. So the file will know it'll update the edit or modified date on the file. But if the file doesn't exist, it'll just create an empty file. So that's what we want. So the name of the file doesn't matter as long as it's an extension .foam. So I'm just going to call it case.foam, but it could be a.foam or b.foam or anything. So if I go touch case.foam, press ls, you can see now I have a file called case.foam. If I go back over here and refresh, you can see I have case.foam, and immediately that .foam extension is associated with PowerView. So if I double click that, that will open up this case in PowerView. So PowerView will know it's an OpenFOAM case. Okay, so this is PowerView. PowerView is not produced by OpenFOAM. It's just a free visualization software, but they have interfaces for very many different like CFD and FEA codes. And it's probably the most used one for OpenFOAM. So when it first opens, you can see this case.foam over here. So you have to press apply to finish actually loading it. So these things here are to do with actually loading the case. So we're going to skip over some of these things. So once we open this, you'll see this is our geometry. And there's a couple of things at the top. So this drop down is to color by different fields, whereas this is to change the representation. So you can show the mesh lines. You can set it to wireframe. You can set the points, and then there's a bunch of other options like feature edge and things like that. So if I just show the mesh, if I hold left click, holding left click is to rotate. Holding right click is the zoom. And if you have I think you can pan if you have a middle click. So you also have your different views here. You can reset. So if I click -Z, it'll just reset the view. Also, if it is a 2D model, you can click this 3D button and it'll switch to 2D motion. So that changes the view. So if you left click now, it just pans, and right click zooms. So just if you wanted to change it, since it's a 2D model, then you can just click 2D and make sure you're set in the Z direction. Then it might be more convenient, but it doesn't matter. Okay, there's a couple of defaults that I like to change when I first open up PowerView. So one is to colors. So if you go edit settings, you don't have to do this, but I find it's easier to visualize results, and it's easier for inserting results into reports. So because there's a gray background, that's a bit annoying if you insert a figure into a report or a presentation and you have like most of the colors, this big gray background. So white is generally easier, because then it will blend in with reporting. You're not wasting ink if you have to print it, but also it probably looks nicer. So if you go to edit settings and then color palette and then the background, click on that and then set it to white. Okay, press apply. And then the other thing is the edges. I think edges are fine as blue, but I think black is probably just a better contrast. Very good. So I will close that. And then the other thing is, by default, the OpenFOAM case reader won't read the time 0. So it won't read the fields at time 0. So if I undo that and press apply, what happens is now I can see my UMP file in my 0 directory. So if I look at U, in this case, it has velocity on the top and 0 everywhere else. So these are the initial conditions. And if I was to look at P, it's just 0 everywhere. So you can see, okay, I need to change the default text color as well. So that's the next thing I'm going to do. If I click a little save button here, that'll just overwrite my defaults, so it'll remember it next time it opens. So the next thing I'm going to do is, while I'm looking at U here, is maybe change the color scheme and the text color. So if I go over here, if I press this, it turns on and off that legend. If I press this button over here, it allows me to edit this color map. So this pops open over here. And if I click this little button in the top corner, it lets me edit settings to do with the legend. So I can just change the color of the text here to black, change volume to black. You can change other settings if you want. Press apply, press OK. Now you can see them. And the last thing is the default color scheme is this blue to red one in Parview, which is fine, but there's often more information can be gotten if you choose a different color scheme. So if you click this little love heart with a folder over here, there's many ones to look at. There's these default ones, and then you can go to all. There's loads of them you can pick from. Parview, or sorry, Abacus, and even Fluent will often use this rainbow. So if I go all, there's something called rainbow. I can even search for it, rainbow. So it'll be something, yeah, like this blue to red rainbow, which is fine as well. But there have been papers published showing that there are scientifically better profiles to use. So there's ones that have matplotlib in the name. There are many other ones as well. But there's ones with matplotlib. I'm going to use this plasma one. Press apply. So what the scientifically derived means, well, basically they're colors that are color schemes that are better for people who may have visual limitations. So for example, if you're colorblind or something like that, then many of these color schemes, a lot of the colors will look the same, so they're not great. So the idea behind some of these matplotlib ones and other ones are that the shade as well as the color will change. So dark is one and light is another one. So the shade is uniformly changing and the color is uniformly changing. So if you go from one increment to another increment anywhere in the scale, it'll have the same relative change in color and shade. But you can use whichever one you want. So I'm going to use that. And then the last thing is this discretize. I'm going to leave that on, but I'm going to tell it to use 12 colors. So rather than having 300 colors of 500, I'm just going to have only 12 of them. So the nice thing of that is we'll be able to see contours in our results. Okay, and I can save this somewhere. I think it's this one here. Save current for all arrays. Yeah, so we click that one, and then that will save everything. And then I can click this little X over there. And we're good. Move my little Parview over. Okay, so that's the case. I can close out of Parview now. So now to run this case, it's already set up. So I just run Eicofone. Eicofone is the name of the solver. Press enter. It's pretty quick. It takes 0.19 seconds on my computer, or rounded to 0 seconds. So if I scroll up and see what it's doing. So many of the Eicofone solvers will look like this. And if you look at the bottom of Fluent in the terminal when it's running, it prints something pretty similar to this. So if I keep scrolling up, okay, eventually I can see where I started the command. So it has a similar heading as before. You can see it's reading in the mesh, reading in properties, reading in the pressure field, the velocity field. And then it starts the time loop. So it goes to the first time step, which is set in system control dict, 0.005. And then it does a couple of calculations. So it solves for velocity in the x direction, ux, velocity in the y direction, uy, solves for pressure twice. So that's what this piezo loop does. Then it goes on to the next time step, which is 0.01. And it does the same thing again. And it basically keeps doing that over and over again. A couple of things to note: it prints out the mean and the max current number, or the CFL number. So the current number, just to remind you, if you have a current number of 1, it means that the velocity of the fluid is such that it is moving 1 cell per time step. So whatever your mesh size is, if your current number, if the max is 1, it means in 1 cell, the velocity, the fluid is actually traveling like 1 cell in that time step. So typically the piezo method, which Eicofone uses, will only converge if your max current number is less than 1. So you can see they've set this case up so that it's close to 1, but it's less than 1. What happens if we double the velocity? Well, the max current number will go greater than 1. So what may happen is the residuals, which we're looking at here, won't converge. They will just explode. So there are methods which let you use current methods greater than 1. So simple methods or pimple methods, you can use current numbers greater than 1. So that's fine. If I ls the directory now, you can see I have a bunch of extra directories. So I have 0.1, 0.2, 0.3, 0.4, 0.5. If I go over here and refresh, you can see them here as well. So what are these? Well, when OpenFOAM writes results, it just makes a new directory. So 0 was our starting time times 0. So then when it wants to write the results at 0.1, it just makes a directory, and then it just writes the P and U fields to that directory. So if I open 0.1 U, it's like before, except now it just lists the 100 values of the velocity vector, or the 400 for the 400 cells. If I skip down or search to the bottom to the boundary field, you can see the boundary conditions are still there. If I open up the P file, so I can close Emacs, but if you want to learn Emacs shortcuts, if you hold Control, then press X, then F, then down here it lets you just type the name of another file, like a little terminal. So I can just write P, press Enter, and then it switches to the P file. So you can see these are just all the pressure values. So I close, holding Control, XC. So let's open this case in PowerView. Again, now that it has results. So PowerView will know to, because this is an OpenFOAM case, it will know to read those as time steps. So after press apply, now I can use the time settings at the top to skip to time step 1, 2, 3, 4, 5. Yeah, so I'm going to look at U. So I'm going to go times U, and then if I skip forward, you'll see that there's some contours. This is the magnitude of velocity here. So I can skip around, and then nothing really happens after 0.4, 0.3, 0.2, 0.1. Pretty much it's reached its steady state at 0.1. So 0.2, 3, and 4, and 5 almost have the same results. You can look at P as well, and they're pretty similar settings. So I can just see that I obviously didn't save my text over here. So I might go back and edit that. So go out to here, and I forgot to press the save button. So if I go black and black, apply and save. Okay. So you can see what happens is you get high pressure in the corner where the fluid's all getting squashed, and then low pressure or negative relative pressure over here. It's been sucked away. So if I go to my U field, you can see the velocity here. So if I look at the X velocity, maybe makes more sense. So it's high here, and then it'll rotate around here. And then Y velocity, it'll start, it's negative coming down here and positive going up. We save that again. It's obviously not remembering it for each new field. And that's fine for now. So I think when I reopen it, it'll remember it for each field. So if I next, if I show just some basic functionality in PowerView. So the way it works in PowerView is you have your results here, and then you can apply what are known as filters, and filters will operate or like modify your whatever's being shown in some way. So you can see there's a little eyeball here. If I click on that, it hides it, and if I click again, it reappears. So all the filters are here. If I go filters alphabetical, they're all here. So some of them have pictures, some of them don't. Some of them apply, and some are grayed out. But some of the common ones are all along here. So if I go through some of the common ones, so you can see here there's one called contour for making contours. It's also clip and slice, so I can click through each of them quickly. So contour, what does that do? Well, if I want to make contours of pressure, if you can just press apply to default settings, and it just makes one contour here, which is like an ISO surface of a particular pressure. So you can see there's one value here. I could add another value of pressure, say like 0, and press enter, press apply again. That gives me another ISO contour. So this one is 0. Or I can just delete all of those and make a range. So I'll click this and say linear range, 10 ISO surface values, press apply, and then it gives me 10 ISO surface values. It's useful in this case, if I turn on my original one, you can't see the ISO contours anymore. So it's useful if I can change the opacity of this. So if I click on any one of these, I can change the opacity. So for my case.foam, if I scroll down, you'll see there's opacity. I can drag that across. And so if I set it to like 0.13, something like that, you can see both of them. So I can turn them on and off. So I'll turn off the contours. Now click back on case.foam because the filters operate on whichever data set you clicked on. So contour now has actually made a new data set, which is these surfaces, and they have their own mesh associated with them. So make sure to click back on case.foam. Next, we'll go to this one, which is called clip. So clip lets us cut through our mesh. So if I just select the default one and I turn off the original case.foam, you can see here that it just sliced through the mesh. I can drag this like this and press apply. I can drag the normal to change the angle and press apply. So you can see I can just cut through my domain. You can click things like invert to keep the other side. And when you're happy with it, you can turn off the show plane so you don't accidentally grab it. So that's what clip is. I'll turn that off, turn back on my original one. I'll try slice. So slice is just like clip, except it just keeps the slice. So in this case, it just keeps what you slice through. So if I click on the Z normal, like one of the presets, and turn off the show plane, just slice through it like that. So for 2D, it's not that useful, but for 3D, it can be useful. I'll close that. You can delete it just like that if you want, but click back case.foam. There's things like threshold. If I click on that, I can just keep cells in a certain range. So any cell which has a pressure that is, say, less than 0, from -4 to 0, I can just keep all of those cells if I wanted. But I guess more usefully would be the glyphs or glyphs and streamlines. So let's do the glyphs. Click back case.foam, go glyphs, set it to be U and U. So the directions are given by the U vector and the magnitude is given by the U vector. So scale by magnitude. And if I just click this auto rescale just to check it's okay, press apply, it'll add some vectors. So now actually you can start to see the form of flow that we get in this case. So you can see that we kind of get one eddy rotating around. So the top is moving from in the X direction with a speed of 0.1 or 1 meter per second, I can't remember, and that causes a rotation in this box basically. There's different settings you can play with there, but I'm going to show streamlines now. So click back in case.foam and go stream tracer. So by default, it'll release them from this line here. So you can move that line wherever you want. I'll just accept the defaults, press apply. So that made loads of streamlines. So I'll probably reduce the number of streamlines there are. So the resolution here is 1000. So I'll press to 100 maybe. Even that's quite a lot. So maybe 20. Press apply. Yeah, that's loads. So I can hide the line. So there's our streamlines, and you can see how we kind of our see-through domain. If you want, then the streamlines, they can often look nicer if you add what are known as ribbons or tubes to them. So you can go filters, alphabetical, tube, and you can actually search for it as well if you go search and just type TUB and then press enter. If you press apply, so when I searched for those tubes, I was not selecting case.foam, I was selecting the stream tracer. So I want to apply tubes to the stream tracers. So you can see it will add nice, like thick tubes that kind of look nicer for visualizations. The number of sides, if we zoom in the tubes, you can see they have a certain resolution. So you can see they're kind of coarse. So instead of 6 sides, maybe we'll give them 40 or something like that. So make nice smooth ones. And if the radius is a bit big, then you can scale the radius maybe 0.0005, make them a bit smaller. So for example, you can play around with these and get them to look whatever you want to look. There's also ribbons. If I go back to stream tracers, I can go filters, alphabetical or search, and then ribbons should be here somewhere, or ribbon. And it's a similar idea. So if I turn off our tubes, you can see that you have these kind of flat ribbons. So they're not that helpful in 2D, but in 3D, they can be nice because the ribbons can rotate as they're flowing around things. But these are just helpful methods to understand or provide insight into the results themselves. Okay, I'm going to close Power View now. So that's the case run. So if you want to change anything, you can just say, for example, change the time step or the viscosity or anything like that. You can just open them up in a text editor, change it, and then save it. The only thing to remember now is if you want to rerun this case, well, the results are already in it, so you need to delete the results first. So if you go remove -rm, and in this case 0.1, 0.2, 0.3, 0.4, 0.5, that will delete all. But you can use wildcards as well, so 0. * would delete all of those. Just be careful when you remove something in the terminal. It doesn't move them to the trash. Once you delete them, they're gone. It's pretty difficult to get them back. So maybe just make backups of things that are important, like models for the assignments and things like that. Okay, so that is the end of this tutorial.